2D vectors in the Cartesian plane. So here we're going to look at vectors in the xy axis, which we've already looked at a little bit. Now, when we draw a position vector starting from the origin, it's going to have an x component, let's call it A, and a y component, let's call it B. So this is just where it lines up on the xy axis. And we can donate the vector by a column matrix AB in this case, because we always put its x coordinate on the top and the y coordinate on the bottom. If this vector started at O and went to the point A, again we can write it as the vector from O to A, which is the exact same thing as the column matrix AB. So remember that if we have a position vector, let's say in this case with x going on the x-axis to 3 and the y to 2, this can be the column matrix 3, 2. But there are also an infinite amount of vectors with the column matrix 3, 2. So it doesn't matter where they begin, they'll all have the same column matrix to represent these vectors as long as they move across 3 units on the x-axis, then up 2 units on the y-axis. Let's have a look at actually adding some vectors on the xy axis. So let's look at that vector 3, 2, where it's gone 3 units along the x-axis and 2 units on the y-axis. And now, so let's call that, it's going to be vector A. Now let's look at the vector that goes 3 units back along the x-axis and 2 units up the y-axis. This will be vector B. So if it went back along the x-axis by 3, we can say that's -3. And if it went up 2, it would have a y component of 2, which we'd expect this to be at 4. And the resultant vector, if we're adding A and B, is just going from the tail from the first one to the tip of the last one. And you might be able to see that, let's just write in this column matrix for A, you might be able to see that that vector, which is A plus B, should just have a 0 x component and a 4 y component. And when we add vectors together using their actual components, it's going to be nice in the fact that all we have to do is actually add the x components together and the y components together. So if we're looking at the vector A plus B, that's just going to be looking at the column matrix for A, which is 3, 2, and adding the column matrix for B, which is -3, 2, and adding these numbers together, so 3 plus -3 is going to give us 0, and 2 plus 2 is going to give us 4, and you can see in fact we do get the column matrix 0, 4, which defines this here. And just in general, we can take the x component and y component of any vector and add it with another x and y component of another vector to get our resultant component, our components for our addition of vectors. So we can just generalize this by saying that the x components added together will be the resultant x component, and the y components added together will be the resultant y component. And let's have a look at another example. We've got our xy axis. And let's look at a vector with x component 1 and y component 2, which means it goes across 1 and up 2. And let's look at another vector, so we'll call that first vector A. And let's look at another vector that has an x component in a negative direction of 3, which means this has to be the point 3, and a y component of 2, which means its column matrix will be -3, 2, and we can call this vector B. Now, how can we get an expression for A minus B? So you might remember from the previous video that if we have two vectors starting at the same point, the subtraction of the vectors of A minus B will be the vector going from the tip of B to the tip of A. So this will be A minus B. And again, just like addition of vectors, we can get it by subtracting the x components from each other and the y components of each other. And because they're at the same height of 2, it's expected that its y component is 0, and its x component should probably be 4, because that's a distance of 3 and that's a distance of 1. But let's just check to make sure. So we can take the vector A minus the vector B to get our A minus B vector. And we're just going to go 1 minus -3, which is going to give us 4, and 2 minus 2 is going to give us 0, and it's exactly what we expected, since that vector goes across 4 to the right and has no y component. Let's just look at an example of scaling a vector. So that's just multiplying it by a constant. So if we have a vector A that has an x component of 3 and a y component of 4, that would have a column matrix of 3, 4. So let's call this vector A. And we times it by 2. We need a vector go in the exact same direction, but double the length. So that vector there would be 2A. And its components is just that scaled factor multiplied by each of the components of the original vector. So we're just going to get 2 times 3, which is 6, and 2 times 4, which is 8, and they're our components for this vector. And we can generalize this by saying if we take any vector A and then multiplied it by some scalar, let's say lambda, this is just going to equal lambda of the x component and lambda of the y component of the vector.